Okay, thank you for the nice introduction, and thank you to the organizers for the possibility to talk here. So I will talk about the geometry of matrix polynomial spaces, and it is a joint work with Johansson and Kokström from Umeå University here in Sweden, as well as with Paul van Doren from Belgium, the University of Leuven. First of all, I dedicate this presentation to the memory of Vladimir Vasilievich Sergeychuk, who was my master thesis supervisor and then mentor and collaborator for many years. Here you can see a picture of us in Barcelona. Here is Vladimir, and here is, for example, Paul van Doren, who is also a co-author of this talk. And Vladimir is greatly missed in the linear algebra and matrix analysis community. It's a big loss for all of us. And now I'm proceeding to the subject of the talk. So as you could see, the talk is about the matrix polynomials, but I will start easy. I will try to explain the idea of this talk using the objects we all know and understand, and namely the Jordan canonical form. Look at the matrix to the left. It is a matrix which has two Jordan blocks, one of size 3 by 3 and one of size 2 by 2, and two parameters, epsilon and delta. If we want to find the Jordan canonical form of such a matrix, then it depends on the values of epsilon and delta. If both of them are 0, then the matrix is already in Jordan canonical form, and it's this matrix below, which is 3 by 3 plus 2 by 2. If epsilon is 0, but delta is non-zero, then the Jordan canonical form of such a matrix is a 4 by 4 Jordan block plus 1 by 1 Jordan block. And if epsilon is non-zero, then we have a single Jordan block of the size 5 by 5. So it tells us that the Jordan canonical form is a discontinuous function of the entries of the matrix. This is something we cannot change, but we can investigate this problem. And we investigate it in the following way. We construct so-called closure hierarchy or stratification graphs. Those are the graphs to the left here. You can see this part, which is a graph, and each node represents all the matrices with the same Jordan canonical form. It's also called an orbit, and it is defined here. So it is an orbit under the action of general linear group, and it's defined as our matrix A multiplied by the invertible matrices S and S minus 1 from the right and left respectively. And then we have an arrow from a node below to the node above. If we can make a small perturbations to the matrices in the node below to get the matrices in the node above, namely in the perturbation that brings us from the bottom one to the middle one is written here. The perturbation with a small delta, and the perturbation from the middle one to the top one can be done with the parameter delta 1 placed in this corner. And then we are in the top node here, which is a 5 by 5 block. So in a more abstract terms, it means that the closure of the orbit means contains another orbit in it. So orbits have so for example, in this case, the closure of an orbit A contains an orbit B, and it means that a small perturbation of the one of the orbit B can bring us to the orbit A. This problem goes back at least to 1978, where it was stated as an open problem by Goldberg and Kashoek in this paper. And lately it was solved independently by two groups of authors. And the solution was in this style. The one orbit is in the closure of another if and only if a certain majorization holds. I'll not go into the details what exactly the majorization should hold here, but it is a condition on the sizes of Jordan blocks of the matrices A and B. So moreover, we also know what are the closest neighbors in such a hierarchies or in such a stratification graphs. And by the closest neighbors, I mean the orbits such that there is no orbit in between. So for example, A and B are the closest if we cannot have the orbit C that can be inserted in this closure property. And this result was firstly derived by Kraft and Processi. And the condition again can be stated in the language of Young diagrams or coin moves if you wish, and it can be interpreted as the following. We look at the example we had before, and now we represent this orbit with the Young diagram, or the pile of coins, of the bottom row containing 3 coins and the top row containing 2 coins. And then when we move this gray coin to the bottom row, so we let it drop, then we are ending up with 4 plus 1, and that corresponds to the further orbit in our chain. And then we can drop the last coin, and then we are ending up at the very top here with the single row. So you can see that those changes can be easily represented by a very simple object. Nevertheless, this might not be the change of the Jordan canonical structure that you are most interested in, because in most of the applications, what people think of is of the splitting and colliding of the eigenvalues. For example, consider our 5 by 5 blocks, blocks that used to be on the top of our chain, but perturb again. We perturb the bottom row of this block with the small parameters epsilon 1, epsilon 5. And see what is happening. If everything but epsilon 5 is 0, then we have 4 by 4 block plus a new eigenvalue. We call it lambda 5. If we have epsilon 4 being non-zero, then we have 2 new eigenvalues. We call it lambda 4 and lambda 5, and so on. And if we have epsilon 1 being non-zero, then the Jordan block of size 5 by 5 splits into 5 different Jordan blocks that corresponds to different eigenvalues, and each of them is of size 1 by 1. So we have just a diagonal matrix with 5 different eigenvalues. Okay. I had an example, actually 2, first with the 1 Jordan block and then with different Jordan blocks for the 5 by 5 matrices. But those examples not cover everything that may happen for 5 by 5 matrices. Nevertheless, this graph here, produced by a software called Stratigraph, which was developed in Umeå, is covering all the possibilities. So all the Jordan canonical forms that are possible for 5 by 5 matrices are presented here, and the arrows means that we can perturb the one below to get the one above. I pulled to the right the Jordan canonical forms that I was using in my examples. So for example, the red one is 5 by 5 Jordan block, and the very top one here is a direct sum of 1 by 1 Jordan blocks corresponding to all the different eigenvalues. So you can recognize this part, and you can see that this is just a small subset of all the possibilities for the 5 by 5 case. And the number of possibilities grows exponentially with the dimension of the matrix. Okay, so a very informal illustration of what it means. Assume that our space is a pyramid, the object that we can all touch and understand. Then we are somewhere on the edge of this pyramid. So here is a pyramid cut into all the pieces, and we are assuming at the middle of this edge. Then an arbitrary small perturbation from this edge can bring us either, okay, I was pointing this edge, so let's say it's this edge that corresponds to the sides. So arbitrary small perturbation from this point, let's say the middle point of the edge, can bring us either to this side or to this side, as well as to the interior part of the pyramid. But if we want to reach the vertex, let's say this one in the bottom or this one in the top, then we need a perturbation at least of the size of half of the edge, right? Because we need to go all the way to the bottom or all the way to the top. So that is the same as we have in our stratification graphs. So to go up into the graph, we can have an arbitrary small perturbations, but to go down in the graph, we need to have a perturbation of at least certain size. This is important for applications because going down means that we are reaching the more degenerate cases, and in many applications you don't want the matrices to become degenerate or singular or have some eigenvalues that collide. Okay, let's increase the complexity, and now we move from a matrix to a matrix pencil or a pair of matrices. So matrix is a polynomial of degree 0, but now we move to a polynomial of degree 1. So the problem is still linear, but now it contains two matrices, and we write it as lambda A plus B. We consider a strict equivalence transformation, which means that now we multiply with non-singular matrices from the right and left, not the similarity transformation, and the orbits are defined respectively. Luckily, we still have a canonical form. Now it's called Kronecker canonical form, and it's recalled here. So the first two types of summands are corresponding to so-called finite and infinite eigenvalues. So those are the eigenvalues. And now we have two new types of summands that are called left and right minimal indices, and they correspond to the singular part of the matrix pencils. Then they are here. Here is a stratification of 5 by 5 matrix pencils, and you can see that the problem is not getting easier, which was expected, because beside the eigenvalues and the perturbations of those, we also have the singular parts coming into the game, and perturbing the singular parts is even more complicated. So the problem, the complexity of the problem grows with the increase of the degree of a polynomial. Okay, let's go even further and try to consider a general case, namely the case of a polynomial of any degree d. So by a matrix polynomial, we mean a polynomial whose coefficients are matrices. We can also think of a matrix whose entries are polynomials. It's the same, but this notation will be more convenient for us. In contrast to the linear case, we no longer have a canonical form. Nevertheless, those invariants, like eigenvalues, multiplicities, we can still define in a different way. We can use Smith's canonical form for this, and here is a definition which I won't go into details with, but I just want to point out that the invariants we investigate are the same, as well as for the minimal indices, we have the strict definition going through the left and right null spaces. I also won't go into the details, and I don't do it because for the purpose of this talk, we will use a tool so-called linearization, and in this case, you can still use the intuition from the matrix pencils and the intuition coming from the Kronecker canonical form. So the canonical form for the polynomial doesn't exist, but the invariants that we investigate are still somehow the same as for matrix pencils, and namely because we are passing to the linearizations. So the investigation scheme has the following steps. First, we need a necessary and sufficient conditions for the matrix polynomial with certain invariants to exist. Then we speak about the so-called strong linearization. Then we need to investigate some properties of this linearization, and then we need to use the hierarchy graphs for matrix pencils. Now I will go through all these steps a little bit more in details. So the first step for matrix pencils didn't exist at all, as well as for matrices. Let's consider this example for the matrices. So does a 7 by 7 matrix with a particular eigenvalues and eigenstructures exist? Well, as long as we have one eigenvalue and we have the sizes of the blocks corresponding to it, and the other eigenvalue and the sizes of the blocks, etc., the only thing we need to check is that the sizes of the blocks correspond add up to the dimension of the matrix. Then we can immediately construct the direct sum and have the matrix. So the canonical form makes it trivial to answer these questions. the same holds for the matrix pencils. But as I said, for the matrix polynomials, we no longer have canonical forms. So if I give you a list of invariants like eigenvalues, their multiplicities, as well as left and right minimal indices, to say that the polynomial with this set of invariants exists is a very untrivial question. And it was answered only in 2015 by Deterandopiko van Doren. And it resulted in the following theorem. So it tells us that giving the list of the invariants, the polynomial exists if and only if we have this equality on those invariants. So basically, the sum of all the invariants is equal to the degree of the polynomial multiplied by the rank of the polynomial. So it's it is resolved. We can at least guarantee the existence. Nevertheless, the proof is not really. It's constructive in a way, but it's not transparent. It's not as a canonical form that you can build a polynomial and see that it actually holds. It's pretty hard to see that it holds if you are giving a polynomial. But the existence is there. Now the second step is about the strong linearization. And what we will use here is so-called first companion form. So instead of investigating a matrix polynomial of degree d, we will move to a matrix pencil, which is a polynomial of degree 1, but we have to pay, and we pay in extending the size. So the polynomial was of size m by n. So every matrix here was of size m by n, but the matrix pencil is now of this size. So we have to increase the size significantly. And if you've never seen this linearization of the first companion form, you might be surprised, but maybe you've been using it without knowing. For example, if you use MATLAB or many other software tools for finding roots of a polynomial, even a polynomial, then what MATLAB does, it actually converts the polynomial to this companion form and computes the eigenvalues of the corresponding matrix. So this is a very common tool to deal with the polynomials, both matrix polynomials, but also scalar polynomials. So this linearization has the same eigenvalues and the same multiplicities as our polynomial, both for finite and infinite. And since it's holds for infinite, we also call it strong linearization. But it doesn't have the same singular structure. Nevertheless, the singular structure is closely related to the singular structure of the polynomial, and namely all the minimal indices, all the right minimal indices are shifted by the value d minus 1. D is a degree. And the left minimal indices remain the same. So they do not remain the same, but there is a very simple relation, which means that we can investigate the linearization instead of the polynomial and still know all the transformations of the invariants for the polynomial. Okay. I recall that we are dealing with the perturbations. So which means that when we perturb now our matrix pencil, then we perturb the whole pencil, including the identity blocks and the zero blocks that we introduced artificially, because the perturbation is now the full perturbation. But that is not exactly what we want. What we want is a perturbation of this style, where only the blocks that correspond to the matrix polynomial coefficients A0, AD are perturbed. That's because we want to preserve the properties, like the physical properties of our problem. So we want the perturbation to correspond to the small perturbations of the polynomials, not to the small perturbations of the full pencil, which is something we introduced to deal with the problem. Luckily, we have this result, which states that whenever we have a small enough perturbation of a linearization, then this perturbation is strictly equivalent to the structured perturbation, the perturbation where only the blocks A0, AD are perturbed. And this means that we can actually reduce our result to our problem to the problem where we perturb the whole linearization, the whole first companion form. It gives us the following result. So for the matrix polynomials, we can essentially reuse the result for the matrix pencils. Like in this example, the stratification of the closure hierarchy of 1 by 2 matrix polynomials is now extracted from the closure hierarchy of 5 by 6 matrix pencils. And we also know how to obtain the neighbors. So I recall you that it's every step here was motivated before in the slides when I was telling you how the invariants are related, as well as why the full linearization corresponds to the structured linearization. So this big graph at the background here is for matrix pencils, and of course every 5 by 6 matrix pencils is then fully perturbed, and we have all the possibilities. But then we extract the nodes because we know how the invariants of the polynomials are changed when we linearize them. So that allows us to extract the proper nodes, and they are all in the top here. They happen to be in the top. And then we can draw the arrows because we have this result on the perturbations. So that if we can achieve something with the full perturbation, we can still achieve something with the structured perturbation. That's why we can induce all the edges here from the edges in the big graph. And that allows us to construct this hierarchy graph for the first companion linearization of the 1 by 2 polynomials. Okay. First companion linearization is not the only one for matrix polynomials. Namely, there are well, many different families, and one of the most popular one is the fiddler linearization family. Here are the other two representatives of this family of linearizations. You can see this one where instead of the coefficients being in the first row, the coefficients now in the first column. This is called the second companion form. And then the other two linearizations where the coefficients are placed in different spots. Like, for example, in this one, the A0 is now placed in the middle and -1 is placed in the first row. It does look like a small change, but it requires the whole theory to be rebuilt. And for a number of applications, people prefer this linearization, for example, to the first companion form. And they are significantly different. In particular, for the 1 by 2 polynomial, even the sizes of these pencils are different. So the first companion form is 5 by 6, as we saw before, while the second companion form, named that is written here, is only 3 by 4. Okay. We also know how the minimal indices are changing for all these linearizations. And we also understand that if we perturb a polynomial, it automatically induces a perturbation on the fiddler linearizations. We just place the perturbations in the proper blocks of our matrices, which gives us a possibility to construct all the graphs for all the possible fiddler linearizations. And they, for the examples I named before earlier, here are those graphs. So the first one is the first companion that we were constructing by extracting the graph from the matrix pencil case. And then using this graph, we construct the graphs for the other fiddler linearizations. So you can see that they all look the same, but the nodes mean different things. Like the node here, the top node here is, for example, 5 by 6 pencil, but the top node here is 3 by 4 pencil. We also notice that these linearizations are also induced graphs from the matrix pencil hierarchy graphs, but for the pencils of the corresponding order, of the corresponding sizes. So for example, for 3x4 matrix pencils, we construct the graph at the background, and we can notice that our stratification of the matrix polynomials, which is now constructed separately, is still a part of the graph for the matrix pencil case. So we can identify it here in the graph. The same holds for the other linearizations, and we can formulate it as a theorem, which tells us that when we have a small perturbation of a fiddler linearization of a matrix polynomial, then we never jump out of the class of the linearizations. So there is always a polynomial Q in this case, such that our perturbed pencil is actually a linearization of this polynomial Q. Moreover, this polynomial Q is actually a small perturbation of our polynomial P that we started with, which means that we are always in the same class, at least if we keep perturbations small. And what does it mean to be small is actually explained in this paper, where some quantitative results on the perturbations are made. Okay, I think that my time is almost out, so I wanted to talk a bit more about the structured case, but I think I'll stop here. Thank you very much.
Thank you.